Hello, this is Coach Key with a video on wavelength and frequency. So let's see what we got here about what do we know about wavelength and frequency. Well, first, the electromagnetic spectrum is a range of all possible wavelengths. Okay, so we're going to look at a few of those today, and we're going to, in just a minute, talk about the symbol for wavelength. The blank is the part of the electromagnetic spectrum we can see, so that would be the visible spectrum. Is the part that we actually see. So finally we get to the part I really like. Talk a little Greek to you here. The symbol for wavelength is kind of a backwards looking H called lambda. And frequency is a weird looking kind of a V slash with an R, and that's called nu. The way to properly say it, of course, is to hold your nose and say the word nu. Nu. It's a nasal. All right, so it's defined just as a point from crest to crest. You also could go trough to trough. So let's look at one of those real quick, and we have a picture here from the book. Sorry, I hope you don't get motion sick. There we go. That's looking at crest to crest is the long wavelength there. The amplitude is coming from the midpoint to the top of the crest. The trough would be the bottom of the wavelength wave. So that kind of gives you a visual there. Let's go back to what we're writing. So the nu is how many cycles or waves to pass a stationary point per time. And most of the time will be in seconds. Okay, sorry about my weird parentheses there. All right, now we get to draw a picture. So again, can you draw a wavelength? Mine is not very good, but there you go. Wavelength would be from point A to point B. That's your wavelength. So your frequency is a little bit harder to draw a picture of that. So some people draw like what they call kind of an eye here, and they're watching point X and they're counting how many goes by per second. Okay, not very good for frequency there, but that's all right. Unit. Now this is very important. Normally we measure this in meters with the abbreviation M, or sometimes we like to use nanometers. And we'll give you that abbreviation as 1 times 10 to the 9th nanometers equals 1 meter. Okay, that would be good to have written down in your notes somewhere. Please write that down. Now the unit for frequency, we got 3 here. Most of the time we do per second. Now Europeans hate it when we do that. We being Americans, they prefer to have second to the minus first. There's another one that we let equal per second, and it's called a hertz. You ever heard of a megahertz phone or a megahertz wavelength? That's where that comes from. All of those mean exactly the same thing, per second. Now, finally, we get to the relationship between wavelength and frequency. As wavelength goes up, frequency goes down. That's called being inversely proportionate. Or, what if wavelength goes down? Frequency would go up. Okay, and we're going to have a formula we're going to use, and I'm going to go ahead and put it here. C equals lambda nu. That is the speed of light which is going to be 3 times 10 to the 8th meter per second rounded. And that's going to equal the wavelength times frequency. Okay, we're going to work several problems with those. So below, we got just a couple of pictures here with radio waves, but I think I like the book picture better. So let's go back to this one. So there's a nice colored picture there. Notice you've got Roy, red, orange, yellow, green, blue, indigo, and violet in that range. This is the rainbow, right? So notice the longest waves are radio waves, whereas the shortest waves would be gamma rays. Remember, some of that goes through lead and concrete. So I really like this. Here's the symbol we're talking about with the lambda being wavelength, measured in meters here. So that kind of gives you a reference point. So kind of neat to see that. Now let's go back to our sheet. Flip the page. Flip it how? All right, Miss Estridge has once again done an amazing job here writing the formula. I would like a little tail on the end of that new. There we go. So let's do this together. Calculate the frequency of a wave that has a wavelength of 2.5 times 10 to the minus 7th. First thing you need to do is, of course, write that formula down. Now, what do you know? You know that C is 3 times 10 to the 8th meter per second, and that equals a wavelength of 2.5 times 10 to the minus 7th meters times some number you don't know. I tell kids to circle the number you don't, or circle the letter you don't know, and that way you put an X there. Now, how do you solve for X? This is all algebra. This is not chemistry. You got to have these math skills. You're going to divide by both sides the 2.5 times 10 to the minus 7th. Now, what happens to your meters? Obviously, they cancel. So plug this in your calculator. How? 3 second EE8 divided by 2.5 second EE negative 7. Be careful. Don't type in subtract here. That's a negative sign down here at the bottom of your calculator, all right? Okay. So when you hit enter, you get 1.2 times 10 to the 15th per second. Don't forget that unit. Okay, feel free to stop this to let kids catch up. But we're going to go ahead and start on the next problem. Calculate the wavelength of the frequency is this number. So here we go. We're going to go ahead and start with C equals lambda nu. Now this time, which one are we looking for? We're looking for wavelength. We work it the same way. 3 times 10 to the 8th meter per second. This time the X is in front. And that number is 1 times 10 to the 3rd per second. So we divide by the 1 times 10 to the 3rd per second. Now what cancels this time? You're right, the per second. So you're going to be left with meters. And that should be 3 times 10 to the 5th meters would equal the frequency. Oh, yes, I'm sorry, would equal the wavelength. There we go. That equals wavelength. I knew something was up there because I saw meters. All right, so let's go ahead and stop there. But there's actually one more before we stop. Let's try one more problem together, and this comes from your sheet that we're going to work on this weekend. One of my absolutely favorite problems is for you to find the color of a wavelength. So everyone grab this packet and look at number 3. That would be one of my absolute favorite questions. So you know you're going to see this on the test. So let's do this one together. C equals lambda nu. So you automatically knew to put that. 3 times 10 to the 8th meter per second. That's going to be given to you. And this time, again, we're looking for the wavelength. Given the frequency is 4.75 times 10 to the 14th per second. Okay, once again, how do you solve for it? Put the number on the bottom, 4.75 times 10 to the 14th per second. So obviously the per seconds cancel out. So now when you punch this in, 4.75 second EE, 14. Be sure to go to scientific here. And I got 6.31 or 32 times 10 to the negative 7th meters. Okay, but we're not done. We're not done. It says give the color. At this point, you need your reference packet. When you flip over on the back of your reference packet, guess what you see down here at the bottom? You see some colors with some wavelengths. So let's look back at our answers. 6.32. So where would 6.32 be on this range? 5.9, 6.5. It'd be right here in the orange region. So my answer is, this is an orange light. Okay, so we'll have some more of those for you to work. But before we leave this, there's one more formula that we really need to look at, and I don't think that's in your other packet. So let's go ahead and go to question number 4. Look at question number 4 on that same wavelength packet. It's on the front of it. So this one, you know, waves are kind of neat in the fact that they can be they can give us color and light from wavelength, but they also heat our French fries up. Remember, who works in a fast food restaurant? If you touch that heat lamp that's keeping your French fries hot, that thing will burn you. So we had to get an agreement, all the scientists had to agree, that light didn't just act as a wave, it also acts as a particle. And this formula accounts for that. It's going to be given to you as well. Energy equals Planck's constant times frequency. So here we go. I'm going to write that out since you haven't seen it before. So energy. Now Planck's constant, I'm going to write down, draw an arrow from up here. That is 6.626 times 10 to the minus 34th. You don't have to memorize that. I'm going to give that to you. But you should already know this letter. That's your frequency. All right? So let's plug this in here. We find the energy. So this time we're finding the energy. And we've got Planck's constant. And that's in joules times seconds. And we have the frequency. Notice you've got per second here, and you've got second. So those cancel, you're going to be left with joules. So you plug that in your calculator. Please watch me do this. Some of you are still struggling with that on your test. 6.626 second EE, negative 34, times 4.75 second EE, 14. And that gives you a 3.15 times 10 to the negative 19th joules. That's a little, very little bit of heat. That you wouldn't even be able to determine that with your finger. So you ever touched a light bulb that had no heat to it? That's what that would feel like. Okay, so we've talked about 2 different formulas today. Hopefully you wrote them both down. I'll try to write it a little neater here. E equals Planck's constant times the frequency. So again, duality of light means that it acts as a wave and it acts as a particle. This accounts for the energy. This is how light has heat. All right, without that you couldn't do it. All right, so I've worked a few examples there. I want you to try the rest of this packet. Again, it won't be due until next week. We'll work on the Bohr model next.